Okay, here we go. Let's start. So we're going to start the next topic, which is sequences and series. So I'll start posting homework today for next Wednesday, and actually we're going to start picking up web work again. Web work will start up again. So not sure if there'll be web work for Monday or not. Watch announcements, watch Blackboard. Maybe, I don't know if I'll make the web work the next one do Wednesday, or I might make one do Monday. We'll see, okay? All right, so sequences and series. So before we do anything in this, we got to have down cold, we got to know what a sequence is and what a series is. So this is it's going to get complicated, it's going to get technical, there's going to be lots of symbols, lots of calculations. And if we don't have this, if we're not grounded in exactly what a sequence and what a series is, then it's not going to go well, okay? So first of all, a sequence. A sequence is an ordered list of numbers. It's a list. It's a list. So we separate with commas, right? So it's a list of numbers. And then the series is where we take all those numbers of the list and we make a giant sum out of them. So we can never lose sight of that. When things get complicated, hard, we're trying to learn to do these problems, we've got to always have this in mind. The sequence is the list. The series is where you take those numbers in the list and you sum them all up. So we'll first talk about sequences here. Then we'll talk about sequences. So the notation for a sequence is this notation here. So we use these like chevrons. I don't know what else to call those. It's not parentheses, it's not brackets, it's not braces, so we'll call them chevrons. That's the notations for a sequence. So what do we mean by that? So when we say a sub I, what we mean is the first in the list, the first number in the list is a sub 1. And the next number in the list is a sub 2, and then a sub 3, etc. So a sub n is the nth term in the sequence. So the subscript tells you which number it is in the list. So here's an example of a sequence. A sub I is 1, 3, 5. Dot, dot, dot means continue like that. Continue like that. So what is A3? What is A3? 5. The 3, A sub 3 refers to the term. 3 refers to which term, right? The third term. So A sub 3 is 5. What is A sub 5? If we assume that the pattern will continue this way. 9. A sub 5 is 9. Okay. What's A sub 85? Okay, so some of you, the wheels start turning, right? So and what you're doing in trying to figure that out is you're trying to come up with a formula that gives A sub n, right? So if you knew what n was, what formula would then, it's kind of like function, right? It's kind of like function. N is like our independent variable. And then A sub n is what the term, the nth term. So maybe you could figure this out. This one is kind of easy, but here's a hint for ones that get harder. Build a table of n and A sub n. So what do I mean by that? So make a little table here. And when you see them side by side, then it starts to, a pattern can be a lot clearer. So when n is 1, A sub n is 1. When n is 2, 3. When n is 3, let's write a couple more out. 4, it's going to be 7. 5 is going to be. So now we can see what how is a sub n determined from n? So what's the pattern here? What do you do to n to get a sub n? So lots of you are saying it. So this is always what? This is 1 less than 2 times n, right? So if you took 2 times n and subtracted 1, you would get a sub n. So what's a of 85 then? So now it's easy because we have this relationship between, given you know it's the 85th term, what is it going to be? 169. Is that right? Because you would take this, you just follow the pattern to be 85 times 2 minus 1. I don't think so. So 85 times 2 is 170, right? And then you subtract 1. Are we good? Yeah. Okay, so then what do we say? A sub n is 2n minus 1. So sequences you can think of, they're very much like a function. But your independent variable is just like the counting numbers. 1, 2, 3, 4. Those are your only values of the independent variable, is like the counting numbers. And then you have sometimes, not always, but sometimes you'll have a relationship that will determine what the nth term of the sequence is. In this case, 2n minus 1. Okay, so then how do we write that? So we can write, so that sequence I wrote before as 1, 3, 5, dot, 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 you can write now as 2i minus 1. And then over here, you can declare where I starts and where it ends. So this, then, is saying that this is an infinite sequence. It has no last term. It has no last term.
Does I always start by default with 1, or is that...
Right, because we want it, it's easiest to think of it that way, because then we can think of this is, you know exactly what 85 is, the 85th term of the sequence, right? If you start, yeah. So you can start it anywhere you want, but I equals 1 is kind of the most convenient, because then you're naming which term it is. Okay, we can also use function notation. A of I, right? Not a sub I. A of I is 2i minus 1, so that's what you're used to with functions. But then we have to specify that I is only the counting numbers. It's not all real numbers like we've thought of functions before. Okay. So, like I said, an infinite sequence has no last term, like the one we just looked at. That one, so if it's just dot, 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 and there's no last term, it's infinite. A finite sequence has a last term. So here's an example of a finite sequence with 20 terms, right? 20 terms, the last term is a 20. Okay. So now you're going to practice. These are harder, but you did good on the first one. So I want you to, here's a sequence B sub I, and here's a sequence C sub I. So I'm going to take attendance while you guys work on these. So write these down. Write these two down. Take 30 seconds to do that. I'm going to take attendance, and then you can chip away at them.
Maybe it's the number squared minus the number times 2. 1. I just thought it was 4.
Okay, so first hint here is don't worry about the negative. Take care of the alternating negative at the end. Okay, that's the first hint. And then second hint is work on the denominator and numerator separately. So hopefully you figured that out. That's really helpful. So if we look at just the numerators. We got 3, 5, 7, 9, 11. So just get this numerator. That's when the first term is 3, second term is 5, third term is 7. What would that be? Anyone get that? So this is a lot like the one we just had. It was 1, 3, 5, 7. So now instead of 2n minus 1, do you see what it is? 2n plus 1. Do you see that's always 1 greater than 2n? So our numerator is 2, or I should say 2i, sorry, 2i plus 1. Okay, denominator. So 1 gives 4, 2 gives 9, 3 gives 16, 4 gives 25, 5 gives 36. What are those numbers? They're perfect squares. Which perfect square is that? 2 squared, 3 squared, 4 squared, and so comparing, so 5 squared is the fourth term, 6 squared is the fifth term. So it is? You add 1 to the term number, and then you square it. How many got that before I started? Pretty good, okay? Those who didn't, does it make sense? Okay, now the last thing is, how do we get this negative? What's this? This sequence is called alternating. It's an alternating sequence because it has every other term is negative. So there's actually several different ways to achieve this. Anyone come up with a way to do this? Yeah. All right, so -1, we know that negative powers depend on whether it's even or odd, right? So -1 to the I, let's check it. So when I is 1, that number is negative. When it's 2, positive, so it just goes away. And that's what we want. And when it's 3, we got 3 negative 1s multiplied together, -1. That's good. When it's 4, positive, etc. So whenever I is odd, you're going to get that -1. Whenever I is even, it just goes away because it's an even number of -1s multiplied together is 1. Does it make sense? So that's it. So we're going to use this later in class, so make sure you write that down. And then this is... so we can write it that way. That will give us those terms of that list that I gave you at the beginning. Questions on that first one? All right, this one. Again, make your table. It's really helpful. So the hint on this one is to look at C3, C5, and C7, because what's happening is on the even term, C4, C2, etc., you're getting some simplification. But these terms actually form the pattern. It's harder to see with these other ones because there's simplification going on to get that final answer. So if we focus on 3, 5, and 7, 3 gives 4/3. 5 gives 16/5. And 7 gives 64/7. So again, split up denominators and numerators. So 3 gives 4, 5 gives 16. Let's do the denominator first. 3 gives 3, 5 gives 5, 7 gives 7. What's the denominator? I. Denominator is just I, right? So now the numerator. 4, 16, and 64. So you may think perfect squares, but you kind of run into a dead end with that. Because this is actually, what? This is like 2 squared, and that's 1 less than 3. This is 4 squared, which is, yeah, that's 1 less than 5. But then you get here, 1 less than 7 is 6, and you get 64, not 36. So the perfect squares isn't working. So we need to see a different way to look at those numbers, 4, 16, 64. Anyone figure it out? Yeah?
2 to the I minus 1.
Okay, so just in general, instead of perfect squares, we're seeing those as? Powers of 2. Powers of 2. Which power of 2 is this? That's the second power of 2. What about this? That's the fourth power of 2. 64 is sixth power of 2. So 3 gives the second power of 2. 5 gives the fourth power of 2. 7 gives the sixth power of 2. So what is it? Say it again.
2 to the power of n minus 1.
Yeah, so you're just going to 2 to the, it's always, the power is always 1 less than the term we're on. Now, we want to make sure that that's right. We want to go back and check C1, C2, C4, C6. Make sure that that works. For instance, let's do C2. C2 is going to be 2 to the 1 over 2, which gives 1. It works. We'll try one more. 2, 4. Let's try C6. 2 to the 5th is 32 divided by 6, right? So I is 6, so 2 to the 5th is 32 divided by 6 is 16 over 3. So it works. All right, questions on those? Questions on those problems? Does it make sense? Okay. So we said a sequence is a list. Sequence is a list. And the series is the sum of those numbers of the list. Burn it in your mind. Burn it in your mind, right? So when things get hard, never lose sight of this. Sequence is the list. The series is taking those numbers of the list and adding them all up. Okay? So here's our sequence. The first one we looked at, 2i minus 1. The series from the sequence is the sum of all of its terms. So I want you to write an expression for that series, just like that you would write for a second grader or a third grader. So if you were to explain to a third grader what a series is, use this example and write it out. You want to explain what a series is to a third grader. Use this example and write out what it is. Remember, you're talking to a third grader, not a calculus student. Write out the series as you would show it to a third grader.
Wait, you want us to write out like a word definition or just how I would explain it?
I want you to write out what the series is, mathematically, what the series is, as you would show it to a third grader. This is really important because we get all these scary symbols, but we've got to know what it means, right? So this is our foundation for what a series is. So how would you write this out? Just mathematically write this out as you would show it to a third grader. What is it? Nope. Okay. Sabrina got it. You should have written this. It's the sum of the terms of the sequence. That's what a series is. You take all the terms of the sequence and you add them up. That's what it is. We're going to get all these scary symbols and algebra and all this scary stuff. But if you don't know that that's what a series is, it's all for naught. Okay, so now we have symbols to abbreviate that. What kind of symbols do we have to abbreviate that? Summation, right? So now write it the way a calculus student would write it. How would you write this for a calculus student? The same series. Okay, you should have written this. So this is our summation, right? Sum up all the terms starting from I equals 1 on forever. And each term is 2i minus 1. So here's the thing. When you see this, whenever you see something like this, you immediately think this. Okay? That's what it means, right? You see this, you always are thinking this, right? Plug I equals 1 into this, that's your first term. Plug I equals 2 into this, that's your second term. Plug I equals 3 into this, that's your third term. And you're going to add them all up. Okay, so generically then, oops, wrong way. Generically, a series has this form. The sum as I equals 1 goes from 1 to infinity of a sub I. That's our just generic notation for a series. Given the sequence a sub I, right? Given the sequence a sub I.
Will we usually be given an equation for A, or will we have to find that out?
It depends on the problem, but often you'll just start with something like this. But like we did examples where you have to figure it out, right? So it just depends on the situation, the problem you have.
Okay.
All right, so I want you to write out series associated with the sequences BI and CI for a third grader and for a calculus student, right? For a third grader and for a calculus student. Go. So you're basically, for BI and CI, you're just writing out this. Okay, so I don't think they're part of the slide. So I think I'll trust that you were able to do that. Just remember the bottom line is, see this, think that, always. See this, think that. Okay, so a partial sum, okay? A partial sum is the sum of the first n terms of a sequence, or the first n terms of a series, right? So a partial sum means we just take the first part of it and only add those up. So we use capital SN for that. So if Sn is the partial sum, it's the sum of the first n terms. Can you write out that in two ways? Using notation and in its meaning. Can you write that out? So what would that look like? Using sigma notation and writing out its meaning. So instead of all the terms of the sum, you just have the first n terms of the sum. So what would change here? What would change for this? The infinity would be n, right? So rather than just going on and on and on for every I value, you only go up to n and you stop. So this would be different just by changing that to n. And then what would be different in your list? So you'd have A1 plus A2 plus A3. But the last one will be AN, right? So if it's that one example. And we know what AN is. What is AN? We could 2n minus 1, right? So you could write stop at AN, or you could write at stop at 2n minus 1. See? Yeah, yes, that's right. Whatever we choose n to be. Okay, so that's a partial sum. A partial sum is just take a part of it, the first n terms of it, of the sum, and that's a partial sum. Okay, so now what we can do is we can take a sum and we can form what's called a sequence. We can go back and form another sequence, the sequence of partial sums. Okay, so the sequence of partial sums is S1, then S2, so S3, and S4. So it's a list of values, and each value is a partial sum. And how does each value in the list compare to the one before? So here's how this works. Like, how does S3 compare to S2? Right. So it's basically A3 added to S2, right? So this is what S1 is just A1. So the first partial sum is just the first term. The second partial sum is the sum of the first two. The third partial sum is the sum of the first three. So each time you go to the next one in the list, you add one more term of the sum. And this makes a sequence, the sequence of partial sums. So what we said was, the first term is A1. What's the second term? The second term is the second partial sum, or A1 plus A2. The third term is the sum of the first three terms. Next term, sum of the first four. And we could use summation notation for those as well, but I just want to make sure it doesn't get too scary, right? So sometimes the summation notation it distracts us with its scariness, right? Just means add up a bunch of things. All right, so summarize. Here we go. A sequence, a series, and a sequence of partial sums. So this is going to be kind of our theme in the next couple of days, of class. There's an initial sequence, and then there's the series, and then from that series you can go back and create a new sequence, the sequence of partial sums. Okay? So what is the sequence? In one word. It's the list. It's the list. So here's a new one. 1, 1/3, 1/5, 1/7, 1/9. Okay, so I want you to write out that series. Write out sigma notation and write out its meaning. For the series, write out sigma notation and write out its meaning. Okay, Chrissy, did you get it? So she said, so sigma, sum, yeah? Sum? Right. So instead of AI, you could have 1 over 2i minus 1. 1 over 2i minus 1. Okay? And that equals Isaac, what's it equal? Right. 1 plus 1/3 plus 1/5 plus 1/7 plus 1/9. That's the series. Okay, so the sequence of partial sums. I want you to watch. Watch this. Don't write. Burn this in your mind. This is where it gets a little bit tricky and dicey, but so just watch. Ready? What's the first term in the sequence of partial sums? 1. What's the second term in the sequence of partial sums? 1 plus 1/3 or 4/3. See that? What's the third term in the sequence of partial sums? 1 plus 1/3 plus 1/5. And it ends up being 23/15. What's the fourth term in the sequence of partial sums? The first 4 terms added together. 176 over 105. And then the fifth term in the sequence of partial sums is the first 5 terms added together. And on like that. Any questions? Does that make sense? Yeah.
Do we ever have like a summation of sequences of partial sums that don't start with term 1 but are like subsets of the series, or not? Like terms 2 through 7?
Yeah, sure. Yeah. And so all you have to do is sigma notation will allow you to do that, right? Like you said, 2 through 7. So I equals 2 to 7.
But traditionally, this partial sum stuff starts with the first 5.
So yes, that would no, because a partial sum is specifically the first n terms of a sequence. So that is like a sum, but really not technically a partial sum. But with sigma notation, if you wanted that, it'd be very easy to define that, like you said, from 2 to 7 or whatever. But partial sums are specifically the first. A partial sum is the first so many terms of a sequence. Was there another question? Yeah.
Unless otherwise explicitly stated, is it okay if we just use the summation notation when you're writing out a partial sums?
Yes, as long as you know what it is, right? Yeah. So we could have used summation, like for this, yes, exactly. For this, is this the fifth? So what? So write that out in summation notation. Write out that 563 over 315. Use summation notation to write that. Go. What is that? That's S5. So I equals 1, 2, 5 of, you could write a sub I, or you could write the formula, which was 1 over 2i minus 1. So that S5 number, that 563 over 315, that's the sum of the first 5 terms, or I equals 1 to 5 of our sequence term. 1 over 2i minus 1. Okay, so there's a relationship between the series and the sequence of partial sums. So the series, think about the series, adding up all the terms. And the sequence of partial sums, which is a list, right? First partial sum, second partial sum, third partial sum, fourth partial sum. So I want you to talk for 30 seconds. What is the relationship between the series and the sequence of partial sums? So this sum of all of them and this list of partial sums. Talk, go. Okay, volunteer. What'd you come up with? What do you think? Partial sums are the accumulation of the series. So what do you mean by that? Yeah, so.
So a sequence of partial sums is just all of the values of the series added up at that point.
Okay. Other ideas or other thoughts? Cody?
Isn't that like saying this is technically how you approximate an integral? It's because we don't know the exact number, so we take the equation and we're adding up until that point. And once you get to that point, you can then go further and with your ends if you wanted.
So you're thinking that the series is kind of like the exact value, and then these are approximations that are getting better and better? Yeah, really, that's really cool. That's good. Yeah.
You can derive the sequence in the series from the sequence of partial sums.
So you can do what?
You can derive it.
Okay. Yeah. So if you're really thinking about the series and the sequence of partial sums, it's kind of like they're the same thing, but just a different form, right? The one is like the whole sum, and the other is a list, and what's happening in that list. As we keep going further and further down that list, right? So what's happening relative to the series? Yeah, it's like approaching it, right? Like it's gonna get closer and closer and closer to the value of the whole sum as you keep going down the list. What idea is that? Limit, right? So the limit. So the limit of the sequence of partial sums, where it's going to eventually get to, if you could walk out the whole list, right, and get to the end of that list, what would the end of that list be? The value of the series, right? So it's the limit. So the value of the series is exactly where the sequence of partial sums is heading to or approaching, and we know that's the idea of limit, right? So the value of the series is the limit of the sequence of partial sums. Again, if you were to walk out that list of partial sums and keep walking it out forever, you would eventually get to this amount that was the sum of the series. So they're kind of like two different ways of expressing the same thing.
The value of the series is equivalent to the limit of the sequence of partial sums.
That's right. That's what that says right there. But that should make sense, right? Because you keep adding one more each time. Each time you go to the next term in the sequence of partial sums, you've added one more from the sum. So if you keep doing that, you're going to get the sum, right? That should make sense. Okay, check Blackboard carefully for homework, whether we have it Monday or not. Happy Friday. Happy weekend.